Dear students, welcome to the chemistry class. Today we are going to discuss about atomic models. In atomic models, in the entrance examination point of view, we have to focus particularly on Bohr's atomic model and wave mechanical model of atom, which is also called as quantum mechanics. First, we will see the details and applications of Bohr's atomic model. This Bohr's atomic model is a combination of Rutherford's atomic model and Planck's quantum theory. In Rutherford's atomic model, the successful aspects were retained by Bohr also. The success of Rutherford's atomic model is regarding the composition of nucleus. By means of his alpha ray scattering experiment, Rutherford has successfully proved that entire positive charge and mass of the atom is concentrated at the center of atom in small space called as nucleus. So that point was retained by Bohr also. The difference between Rutherford's atomic model and Bohr's atomic model is regarding the position of electrons in the atom. According to Rutherford's atomic model, electrons were supposed to be rotating around the nucleus in elliptical paths, just like planets are rotating around the sun. But in that, the problem is when electron is moving around the nucleus in elliptical path, what happens during its course of journey, sometimes it will be coming nearer to the nucleus and sometimes it will be moving away from the nucleus. So what happens, as the distance between electron and the nucleus decreases, to overcome the nuclear force of attraction, the electron has to increase its speed, and when it is moving away from the nucleus, it has to decrease its energy. So during part of the journey, sometimes it has to undergo acceleration and sometimes it has to undergo deceleration. But whenever any particle undergoes acceleration or deceleration, it will lose energy. And when energy of electron is lost, at some point of time, it may come in contact with nucleus, which leads to the process of annihilation. That is, conversion of mass into energy should take place. But in practice, as it is not happening, we should say electron is not rotating in elliptical path as suggested by Rutherford. So here Bohr has modified. Instead of taking elliptical shape, has taken circular shape. So the modification is electron is moving around the nucleus not in elliptical path as suggested by Rutherford, but in circular path. So when electron is moving in a circular path, its distance from the center of nucleus always remains constant. When the distance remains constant, electron can move around the nucleus with a constant speed. Therefore, loss of energy of electron will be minimized. So that is why Bohr says whenever an electron is moving in an orbit, its energy remains constant. That's why these orbits are also called as stationary orbits. So how many orbits are possible for any atom? Theoretically, for any atom or for any element, number of orbits possible are infinity. Practically, that number has been restricted to 7. So the orbits can be designated either with numbers like 1, 2, 3, 4 up to 7, or you can make use of alphabets like K, L, M, N, O, etc. K stands for the first orbit, L stands for second orbit, M stands for third orbit, so on. So these designations you can make use while solving the problems based on this Bohr's atomic model. Now, when so many orbits are available where the electron can stay, that is pre-decided by means of a condition called quantization of orbit condition. Mathematically, the quantization of orbit condition can be represented like this. MVR is equal to NH by 2 pi. This product MVR represents angular momentum of the electron. H stands for Planck's constant. N stands for number of the orbit. So, electron can stay only in that orbit where its angular momentum value is a multiple of h by 2 pi. So, this condition is called as quantization of the orbit condition. When externally energy is supplied, electron can move from lower orbit to higher orbit. The process is called as excitation. But electron cannot stay in the higher orbits forever. According to the condition of quantization of orbit, it should come back to its original orbit. So, that return journey of electron is called as de-excitation. During the process of excitation, energy will be absorbed, whereas during the process of de-excitation, energy will be emitted in the form of electromagnetic waves, which are responsible for the formation of spectral lines. The amount of energy absorbed or amount of energy released is calculated by using the relation delta E is equal to E2 minus E1 is equal to h nu. That means frequency of emitted radiation is directly proportional to difference in the energy levels of the orbits between which electronic transition takes place. Here E2 stands for energy of the higher orbit, E1 stands for energy of lower orbit. So, these are the basic postulates of Bohr's atomic model, by making use of which we can explain the formation of various spectral lines in hydrogen, as well as we can derive equations by using which we can calculate important data regarding electron. Applications of Bohr's atomic model. The first application is explanation of hydrogen spectrum. Now, what is meant by this explanation of hydrogen spectrum? When you refer to the hydrogen spectrum, a simple element like hydrogen has emitted number of spectral lines in three parts of electromagnetic spectral region. Some were observed in ultraviolet region, some were observed in visible region, and some were observed in infrared region. Now, the question is how a simple element like hydrogen can emit so many number of spectral lines, that too in three different regions of electromagnetic spectrum. For that, answer can be obtained by making use of Bohr's atomic model. So, for any atom, theoretically, how many number of orbits are possible? Infinite number of orbits are possible. But practically, that number has been restricted to 7, and they can be numbered like this. Each orbit is indicated in the form of a straight line here. So, in hydrogen, electron will be initially present in the first orbit. When energy is supplied to it in the form of heat energy or in the form of electrical discharge, by absorbing the energy, electron can move from its original orbit to higher orbit. So, depending on the quantity of energy absorbed, either it can move from first orbit to second, third, fourth, or still higher orbit. Generally, if electron crosses the seventh orbit, it is out of the control of nuclear force of attraction. So, the energy required for that purpose is taken as ionization energy. But if I assume that the electron has absorbed sufficient energy to reach only seventh orbit, there it cannot stay forever. Again it should come back to the first orbit. The process return journey can be called as de-excitation. The process of de-excitation either can take place in a single step or in multiple steps. Accordingly, number of spectral lines will be observed. Say for example, electron can jump straight away from 7th orbit to 1st orbit, or in stages like from 6th to 1st, 5th to 1st, 4th to 1st, 3rd to 1st, 2nd to 1st. All these transitions lead to the formation of spectral line observed in Lyman series. This region is ultraviolet region. Similarly, the electron can jump from higher orbits to second orbit, stay there for some time, and again can come back to the original orbit. So, the various transitions possible are represented like this, which fall into the next series, that is Bhanu series. Similarly, electron can jump from higher orbits to third orbit in so many ways, which lead to the formation of next series of spectral lines, that is Paschen series. Similarly, other series of spectral lines can be observed. Now, in the discharge tube, we cannot take a single atom of hydrogen. We take some specific quantity of the gas, which consists of a large number of atoms, and each atom may not absorb same quantity of energy. That is why very large number of spectral lines were observed in case of hydrogen spectrum. Now, for a particular transition, how many spectral lines are possible? That you can calculate by using this relation. Number of spectral lines observed is equal to sigma delta n, that is sigma n2 minus n1. n1 stands for lower orbit number, n2 stands for higher orbit number between which an electronic transition takes place. Say for example, if electronic transition is taking place from 7th to 1st orbit, maximum number of spectral lines that can be observed, we can calculate by using this relation. Say number of spectral lines is equal to sigma n2 minus n1, 7 minus 1, that is sigma 6. Sigma 6 you can calculate like this, 6 plus 5 plus 4 plus 3 plus 2 plus 1. The total number comes out to 6, 10, 15, 21. Like that, how many spectral lines are possible in a particular transition can be calculated. This is what we call explanation of hydrogen spectrum. The next most important application is derivation of velocity, radius and energy of electron. So, electron is a very small and invisible particle. In the atom, it is moving around the nucleus with how much velocity it is moving and at what distance it is present from the center of nucleus and how much of energy it has been associated with. All these parameters can be calculated by making use of Bohr's atomic model. For that purpose, visualize like this. This is the nucleus in which Z number of protons are present. Each proton carries 1 unit of positive charge. Let us represent it as plus E. Round that nucleus, electron is moving, say, in the first orbit. Let us assume that m is the mass of electron, v is the velocity of electron, and r stands for distance of the electron from the center of nucleus, which is literally equal to radius of the orbit, because orbit is in the form of a circle. Now, what are the forces operating on the electron? One is a nuclear force of attraction, which can be calculated by using Coulomb's law, that is Q1 Q2 by D. Q, in place of Q1 we can take the charge of nucleus, which is Z into plus E, and charge on electron can be taken as minus E, distance R, so R square. So this comes out to minus Z E square by R square. Now this nuclear force of attraction is balanced by the centrifugal force of electron. As electron is moving in circular path, it will be associated with centrifugal force, which will act in the tangential direction, and that force we can calculate by using the relation mv square by r. As these two forces are equal in their magnitudes, we will equate the magnitudes. Z square by r square is equal to mv square by r, and this can be simplified as mv square is equal to Z E square by r. Now, by making use of Bohr's atomic model, we will make use of the condition of quantization of the orbits, that is mvr is equal to nh by 2 pi. Let us call it as equation number 4. Dividing third equation with the fourth equation, mv square by mvr is equal to Z E square by r by nh by 2 pi. The common terms get cancelled and v comes out to 2 pi Z E square by nh. This is the relation used for the calculation of velocity of electron. In this expression, Z stands for atomic number of the element, E stands for charge of electron, N is number of the orbit, H is Planck's constant. Now, in this expression, except Z and N, rest of the things are constant values. So, when you substitute corresponding values, this equation can be simplified as V is equal to (2.18 into 10 power 8) meters per second, or in terms of centimeters, you can take it as 2.18 into 10 power 10 by n into z centimeters per second. This is the MKS value, this is the CGS value. By using this simplified forms, straight away we can calculate velocity of electron in various orbits. From this expression, what we can say, velocity of electron is directly proportional to atomic number, and velocity of electron is inversely proportional to number of the orbit. With increase in the number of orbit, velocity always decreases, whereas with a decrease in number of the orbit, velocity of electron always increases. So these relations particularly you have to keep in mind for working out the problems. Now, substituting the velocity expression, say equation number 5, in the fourth equation, what we get? M into, in place of V, now you can write 2 pi z e square by nh into r is equal to nh by 2 pi. This on further simplification can be condensed as r is equal to n square h square by 4 pi square m e square into 1 by z. So this is the expression used for the calculation of radius of the orbit. In this expression also, except n and z, rest of the things are constant values. N stands for number of the orbit, h is Planck's constant, m is mass of electron, e is charge of electron, z stands for atomic number of the element. Now, we can substitute the constant terms here. Then, this equation can be simplified as r is equal to 0.53 into n square by z. This value is in terms of angstrom units. This condensed relation can be used for the calculation of radius of orbit. So from this expression, what we can conclude is radius of the orbit is directly proportional to number of the orbit and inversely proportional to atomic number. As n value increases, radius increases. As z value increases, radius will decrease. So these two relations particularly are to be kept in mind for solving number of problems based on Bohr's atomic model. Next, calculation of energy of the electron. As the electron is continuously moving around the nucleus, it is associated with both the potential energy as well as the kinetic energy. So, the total energy of electron can be taken as a sum of potential energy and kinetic energy. The potential energy is calculated by using this relation Q1 Q2 by D. Q1 stands for charge of the nucleus, Q2 stands for charge of the electron. So, plus Z into E into minus E by distance is R. Kinetic energy can be calculated by using the relation half mv square. So, this comes out to minus Z E square by R and this half mv square. But in the very beginning, when we have equated the magnitudes of nuclear force of attraction and centrifugal force, we proved that mv square is equal to ze square by r. Now make use of that relation here. So this can be condensed as minus ze square by r plus half into ze square by r. This can be further compressed as minus ze square by 2r. In this expression, if you substitute the value of r, that is 2 into n square h square by 4 pi square m e square into 1 by z, it comes out to finally minus 2 pi square m e power 4 by n square h square into z square. So, in this expression, except z and n, rest of the things are constant values. And because of this negative sign, with increase in n value, the energy of electron increases. And with increase in z also, atomic number, the energy of electron will increase. On substituting these constant values, this can be condensed as minus 13.6 by n square into z square electron volts. So, by using this relation, we can calculate energy associated with the moving electron. With increase in n value, that is number of the orbit, energy of the electron always increases. And as per the requirement, the electron volt unit of energy can be converted into other forms of energies, other units of energies. Like you can convert electron volts into joules, calories as well as ergs. This is the second most important application of Bohr's atomic model. You can calculate the total energy, potential energy, kinetic energy of electron. You can calculate the velocity with which electron is moving around the nucleus. We can calculate the distance of electron from the nucleus. Then the third application is it gives theoretical proof to Rydberg's equation, which is beyond the scope. Just remember the statement. Theoretical proof can be given to Rydberg's equation by making use of Bohr's atomic. That is the success story of Bohr's atomic model. But Bohr's atomic model also has got certain limitations. What are those limitations? The major limitation is Bohr's atomic model is applicable for uni-electron species. Uni means one or single. That means we can apply Bohr's atomic model to either hydrogen or hydrogen-like species like He plus, Li plus 2, which contain only one electron. For them, we can apply Bohr's atomic model. But it fails in case of multi-electron species. Multi means if more than one electron is present, that will be taken as a multi-electron species. That is the biggest limitation of Bohr's atomic model. Then second limitation is it explains the various spectral lines formed in hydrogen spectrum. But same hydrogen spectrum, when it is observed in the presence of a strong external electrical field or strong external magnetic field, it has been observed that each spectral line gets divided into number of lines, pack of lines. That splitting of spectral lines in the presence of external electrical field or external magnetic field is called as a fine spectrum. Fine spectrum means splitting of individual spectral lines in hydrogen spectrum into pack of lines in the presence of external electrical field or magnetic field is called as fine spectrum. So, when fine spectrum takes place in the presence of electrical field, then it is called as a Stark effect. When the splitting takes place in the presence of external magnetic field, then it is called as a Zeeman effect. And Bohr's atomic model fails to explain these two effects. That is the second limitation. Third limitation, which is not yet cleared even today, is regarding the stability of atom. Now, Bohr's atomic model says when electron is moving around the nucleus in an orbit, its energy remains constant. But electron is a minute particle. When it is moving around the nucleus, it is continuously and constantly doing work. And whenever work is done, its energy should come down. And at some point of time, energy of electron should be reduced and it should come in contact with the nucleus, which is not taking place practically. So, regarding the stability of atom, still some clarity is missing, which cannot be explained by making use of Bohr's atomic model. So, these are the major limitations that can be attributed to Bohr's atomic model. To overcome the limitations of Bohr's atomic model, next came into picture Sommerfeld's atomic model, but it has failed. And in its place, what we are making use called wave mechanical model of atom came into existence. This wave mechanical model, also called as quantum mechanics, is actually a combination of three different concepts. One is called de Broglie's wave theory. Heisenberg's uncertainty principle, and Schrodinger's wave equation. Combination of all the three is collectively called as a wave mechanical model of atom. Now let us take one by one. First one, de Broglie's wave theory. What it says is matter has dual nature. That is the simplest way of representing de Broglie's wave theory. Matter has dual nature. What is meant by that? Dual means a double character. Double in the sense matter can behave as a particle as well as a wave at a time. But this is true in case of microparticles. Micro means small particles, that too moving with a high velocity. This statement is not applicable or partially applicable for macro particles. Macro means large particles moving with a less velocity. In case of microparticles moving with high velocity, the waves associated with the particle or matter are called as matter waves. So when you are saying a wave, it will have wave properties. One of the wave properties is wavelength. To calculate the wavelength of matter waves, de Broglie has given a relation called de Broglie's equation, which is represented as lambda is equal to h by mv. Here, lambda stands for wavelength of the waves, matter waves associated with the moving particles. H stands for Planck's constant. M stands for mass of the particle. V is the velocity of the particle. Right? The product of mass and velocity can be taken as a momentum also. So this equation can also be represented as lambda is equal to h by p, where p stands for momentum of the particle. Werner Heisenberg's uncertainty principle. What it says, initially it says it is impossible to calculate the exact position and velocity of a moving particle like electron. If that is the case, atomic structure comes to an abrupt end. But from impossible, he continues and makes it possible to predict the location of electron by making use of the principles of probability. When you cannot calculate with accuracy, we can calculate at least uncertainty in the calculation. From uncertainty, certainty can be calculated, because the sum of certainty and uncertainty is always equal to unity, that is 1, or in terms of percentage 100%. So initially Heisenberg says it is impossible to calculate the exact position and velocity, but continues to say that you can calculate the uncertainty in the calculation of position and velocity, and the corresponding relation is called as Heisenberg's uncertainty equation, which is represented as m delta x delta v is equal to h by 4 pi, or you can write it as delta x delta p is equal to h by 4 pi. Here m stands for mass of the electron, delta x stands for uncertainty in position, delta v stands for uncertainty in velocity, h is Planck's constant. In this alternate form, delta x is same, that is uncertainty in the calculation of position, delta p stands for uncertainty in the calculation of momentum. So by using this equation, first we calculate uncertainty, and from that certainty and calculation can be identified by using the principles of probability. Schrodinger's wave equation. Schrodinger's wave equation is a combination of de Broglie's wave theory, Heisenberg uncertainty principle plus applied mathematics. Schrodinger has combined de Broglie's concept and Heisenberg's concept and applied the principles of calculus to derive an equation called as Schrodinger's wave equation. It is represented like this. The symbol is called as dou and is pronounced as dou square. Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0. This equation is called as Schrodinger's wave equation. This can also be represented as dou square by dou x square plus dou square by dou y square plus dou square by dou z square into psi plus 8 pi square m by h square into E minus V into psi is equal to 0. This part can also be represented like this, del square. This is called a del operator. So this equation can be represented simply as del square psi plus 8 pi square m by h square into E minus V into psi is equal to 0. Now this is a mathematical equation called a partial differential equation of order 2 with 3 variables. When this equation is solved, you will get a total of 6 solutions. Out of 6, 3 solutions are real in nature and remaining 3 solutions are imaginary in nature. The real solutions of Schrodinger's wave equation are called as eigenfunctions, and later this term eigenfunction is replaced with a quantum number. So, what are quantum numbers means we can say the real solutions of Schrodinger's wave equation. So, the 3 quantum numbers that can be calculated by solving Schrodinger's wave equation are principal quantum number, azimuthal quantum number, magnetic quantum number. So, the quantum number that is not obtained by solving this equation is spin quantum number. 16. How many electrons are present in the M shell of an atom of an element with atomic number 24? Atomic number 24 corresponds to chromium. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d, 5. So, M shell means the third orbit. Number of electrons present in the third orbit are 8 plus 5, 13. So, correct answer is option D. Number 17. The product of uncertainty in velocity and uncertainty in position of a microparticle of mass m is not less than in which of the following? So, here we have to make use of uncertainty principle, Heisenberg's uncertainty principle, according to which m delta x delta v is equal to nh by 2 pi. So, here uncertainty in velocity and uncertainty in position product is required. Delta x delta v is equal to nh by 2 pi into m we can write. So, n value has to be compulsorily an integer value. So, first, second and fourth are ruled out, only option left out is third option C. C is the correct answer for this question 17. 18th question. Assertion and reason are given. Assertion is atoms with completely filled and half filled subshells are stable. Reason, completely filled and half filled subshells have symmetrical distribution of electrons and have maximum exchange energy. So, assertion is correct, reason is also correct, and the given reason is a correct explanation for the given assertion. Therefore, option A can be taken as the correct answer. 19th question. Which of the following set of quantum numbers is correct for an electron in 3D orbital? 3D orbital means n value is 3, L value is 2, M value can range from -2 to +2 including 0, S can be either +half or -half. So, we have to check for the correct options based on this information. N value 3 is there in all the options. L value 2 is present in A, C and D, and M value range is exceeding in case of A, B and D. So correct option is C. C is the correct answer for question number 19. 20th question. If the kinetic energy of a particle is reduced to half, de Broglie's wavelength becomes what? De Broglie's wavelength and kinetic energy are inversely proportional to each other. This is the mathematical relation. So, if kinetic energy is reduced to half, de Broglie's wavelength increases by root 2 times. So, correct option is D. 21. In an atom, the order of increasing energy of electrons with quantum numbers. Set of values are given. Energy of an electron is calculated by means of n plus L value. The one with higher n plus L value will have higher energy. So, if you take the first case, n is given as 4, L as 1. So, n plus L value will be 5. In second case, the total value is 4. In third case, the total value is 5. In fourth case, it is 4. So, we are getting same values in set 1 and set 3. When we cannot differentiate with the n plus L value, we should go with the n value. The one with the lower n value is associated with the lower energy. So, between first option and third option has a lower energy than first option. So, correct answer option is, this is a increasing order. So, 1 less than 3 less than, between second and fourth also, fourth one has a comparatively lower energy because its n value is less. So, correct order is 1 less than 3 less than 4 less than 2 less than 4. So, this set is present in the option C. C is the correct answer for this question. The number of angular and radial nodes of 4D orbital respectively are. Number of angular nodes is equal to L and radial nodes is equal to n minus L minus 1. So, for a 4D orbital means for D, L value is 2. Therefore, angular nodes number is 2. Coming to calculation of radial nodes, in place of n we have to take 4 minus L value is 2 minus 1. So, that comes out to 1. 2, 1 is the correct set of answers. So, for this question, option D is the correct answer. 23rd question. The number of radial nodes of 3s and 2p orbitals respectively are. The radial nodes are calculated by the relation n minus L minus 1. So, for 3s, 3 minus, for s L value is 0 minus 1. So, that comes out to 2. Whereas, for 2p, n value is 2, L value for p is 1 minus 1. So, that comes out to 0. 2, 0 is the correct set for this question, which is present in option B. 24th question. The basis of quantum mechanical model of an atom is C. Dual nature of electron is the correct answer. 25th. In photoelectric effect, if the energy required to overcome the attractive forces on the electron, that is work functions of 3 elements are given, lithium, sodium and rubidium are 2.41, 2.30 and 2.01 respectively. The work function of potassium could approximately be in electron volts. This work function value decreases down the group. The elements mentioned are present in first A group. The elements present in first A group are lithium, sodium, potassium, rubidium, cesium and francium. So, lithium value is given as 2.41, sodium value is given as 2.30, rubidium is given as 2.09. Potassium value should lie in between 2.3 and 2.09. So, the correct value can be taken as equal to B, 2.20. The 26th question, the quantum number which explains the line spectra observed as doublets in case of hydrogen and alkali metals and doublets and triplets in case of alkaline earth metals is. The correct option is B, azimuthal quantum number. Which one of the following frequencies of radiation has a wavelength of 600 nanometers? So, here if we find out the frequency with the given wavelength, that will be the correct option. Frequency is calculated as c by lambda. Velocity of light, if you take in meters, it will be 3 into 10 power 8. Wavelength is given in terms of nanometers. Convert it into meters by multiplying with 10 power minus 9. So, on simplification, it will become 0.5 into 10 power 15, or it can be written as 5 into 10 power 14 hertz. So, this value is present in option D, that can be taken as the correct answer. According to Bohr's theory, which of the following values of angular momentum of hydrogen atom are not permitted? According to Bohr's atomic model, angular momentum of electron MVR has to be an integral multiple of h by 2 pi. If we get a fractional value, that is not a permitted value. In the first option, n value comes out to 2.5, a fractional value, hence it cannot be the correct answer. So, for 28th question, correct option is A, which is not permitted, means first option can be taken because their n value comes out to a fractional value. Which one of the following transitions of an electron in hydrogen atom emits radiation of the lowest wavelength? Given options are infinity to 2, 4 to 3, 2 to 1 and 5 to 3. Is observed in case of Lyman series, and for Lyman series n1 value is 1. This is present in option C, which can be taken as the correct answer. 30th question, the wavelengths of electron waves in two orbits are given as 3:5. The ratio of kinetic energy of electrons will be. The kinetic energy and wavelength, they are inversely proportional to each other. According to de Broglie's wave equation, lambda is inversely proportional to square root of Ke. Lambda 1, lambda 2 are taken as the wavelengths. The ratio is given as 3 by 5. That will be equal to square root of Ke2 by Ke1. So, we need to calculate Ke1 by Ke2 value. So, it has to be inverted and then squared. That comes out to 25 by 9, or 25:9. So,